Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the fifth numerical on baseband shaping for data transmission. Let me read out the question first. An audio signal of bandwidth 4 kHz is sampled at a rate 25% above the Nyquist rate and quantized. The quantization error does not exceed 0.1% of the signal peak amplitude. The resulting samples are then encoded and transmitted by 4 array pulses. Part A of the question says, determine the minimum number of 4 array pulses required to encode each sample. Part B, determine the minimum transmission bandwidth required to transmit this data with 0 intersymbol interference. Part C, if the Nyquist criterion 4 array pulses with 25% roll-off are used to transmit this data, determine the transmission bandwidth. Right. Let us now understand the question. We have an audio signal of bandwidth 4 kHz and it is sampled at a rate 25% above the Nyquist rate. I'll start the solution with that part first. Let us first write down what is the signal bandwidth, which is f0 equals to 4 kHz. We are told it is sampled at a rate 25% above the Nyquist rate. So, I'll first find the Nyquist rate. We know that Nyquist rate is equal to 2 times the highest frequency component of the signal. So, this is equal to 2 into 4 into 10 power 3, which is 2 multiplied by f0. This is 8 kHz. Therefore, the sampling rate, as we are told in the numerical, is equal to 0.25% greater than the Nyquist rate. So, this is 1.25 multiplied by the Nyquist rate. That is 1.25 multiplied by 8 kHz, which is equal to 10 kHz. This is the sampling rate of the audio signal. Coming to the second sentence, you note the quantization error is said to not exceed 0.1% of the peak signal amplitude. Let us now find out what is an expression for quantization error. We know that the quantization error is equal to delta divided by 2, which is also expressed in terms of the peak signal amplitude as x max divided by L. Now, in the numerical, we are told the quantization error does not exceed 0.1% of the peak signal amplitude. So, the maximum value of the quantization error should be 0.1%, which is 0.001 into x max. So, we have now an equation x max divided by L equal to 0.001 x max. I can write this as x max divided by 1000, which is x max divided by L. Therefore, the value of L is equal to 1000. However, we have known that L here represents the number of quantization levels and the number of quantization levels must be a power of 2. So, L here is equal to 1000, but this should be expressed in terms of 2 power n. If I take n equal to 1, this indicates L equal to 2 less than 1000. If I take n is equals to 5, this indicates L equal to 32 less than 1000. If I take n equal to 9, this indicates L equal to 512, which is still less than 1000. So, when n is equal to 10, we get L as 1024 and this is greater than 1000. So, we should now select L as 1024 because this now represents the value of L in power of 2. Therefore, we now say select L as 1024. And as we already have calculated, for this value of L, we find the value of N as 10 bits. Please note, this is 10 bits per sample. Right. With that, let us now start going to part A of the question. Part A of the question says, determine the minimum number of 4 array pulses required to encode each sample. Let us now first understand how many bits of information is conveyed in each 4 array pulse. So, we say each 4 array pulse conveys log 4 to the base 2 bits of information. We know that log 4 to the base 2 is nothing but 2. So, each 4 array pulse conveys 2 bits of information. Once we find how many bits of information is conveyed per each 4 array pulse, we can now find the minimum number of 4 array pulses required to encode each sample by simply dividing the number of bits divided by the number of bits of information conveyed per each 4 array pulse. So, I will write minimum number of 4 array pulses required to encode each sample is equal to the total number of bits per sample divided by the number of bits conveyed per each 4 array pulse. Therefore, this is equal to 10 divided by 2, therefore 5 4 array pulses per sample. This is the minimum number of 4 array pulses required to encode each sample. That completes part A of the question. Let us go back to part B. In part B, we are asked to determine the minimum transmission bandwidth required to transmit this data with zero intersymbol interference. Please note, we are asked to calculate minimum transmission bandwidth, which is nothing but B naught. So, let us now work on that. We start by identifying the sampling rate of the analog signal as 10 kHz. Therefore, the total number of 4 array pulses would simply be the number of pulses per each sample multiplied by the sampling rate. Therefore, I can now write the total number of 4 array pulses is equal to 5 multiplied by 10,000. This is equal to 50,000 4 array pulses. Once we find the total number of 4 array pulses, the minimum transmission bandwidth is simply the total number of 4 array pulses divided by 2. Therefore, the minimum transmission bandwidth is given by total number of 4 array pulses divided by 2, which is 50,000 divided by 2 equal to 25 kilohertz. This is the answer for the minimum transmission bandwidth. Please note, there is an alternative way of finding the same, and I will solve using that method as well. Let us now take capital T as the duration of each 4 array pulse. To represent 10 bits, we will require 5 pulses. So, 1 Ts is equal to 5 T. Please note, Ts here stands for the sampling interval and capital T represents the duration of each 4 array pulse. From the raised cosine spectrum, we know that the minimum transmission bandwidth B naught is given by 1 divided by 2T. Please note, I should not write it as TB here. If I write TB, then it would mean the system is a binary system. Here, we are very clearly told it is a quaternary system. Therefore, I should write it as 1 divided by 2T. From the above equation, I can write T as Ts divided by 5. So, B naught would be equal to 1 divided by 2 multiplied by Ts divided by 5, which is equal to 2.5 into Fs. Now, Fs is equal to 10 kilohertz. Therefore, the value of the minimum transmission bandwidth is equal to 25 kilohertz, which is the same as what we obtained using the alternate technique. Lastly, I will move on to part C of the numerical here. Part C of the numerical says, if the Nyquist criterion 4 array pulses with 25% roll-off are used to transmit this data, determine the transmission bandwidth. Please note, here we are given a roll-off factor of 25%, which is alpha equal to 0.25. We are asked to find the transmission bandwidth, which is capital B. So, I will start part C by writing given alpha equal to 0.25. Then, I will write an equation that relates the transmission bandwidth, the minimum transmission bandwidth, which is B naught, and alpha as B equal to B naught into 1 plus alpha. Let us now substitute all these values. B naught is 25 kilohertz and alpha is 0.25. Therefore, the transmission bandwidth is equal to 31.25 kilohertz. This is the answer for part C of the numerical. Well, with that, we have come to the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.